So today we are going to take a discussion on open channel flows. You have already learned about the pipe flow in your earlier course of fluid mechanics. That is the basic fluid mechanics. Now we will consider another aspect where the flow takes place in open channels. Now open channel flows are very practical oriented situations where the flow is taking place in natural channels like rivers or creeks and also artificial channels. So we are going to consider the following topics in our discussion today. First we will have a little introduction to the open channel flows and a comparison between the open channel flow and the pipe flow, followed by the various classifications of open channel flows. Like the pipe flows, the open channel flows are classified into various categories of flow. Then you will receive a little information on the various terms and definitions as well as the geometric properties of some standard channel sections. Then how the velocity varies within the open channel as well as the pressure distribution in an open channel will be considering. Followed by this, we will take up the basic equations that are available for the analysis of open channel flow. And these equations are, most general equations used are Chezy's equation and the Manning's equation. So we will be considering these two equations. Lastly today, we will initiate a discussion on the uniform flow and the uniform flow computations. So let us proceed. What an open channel flow is. So any flow where the liquids flow with a free surface, unlike a pipe flow, that means there must be an interface between the water surface or liquid surface and air, that is the atmosphere above it. So that is called as an open channel flow. Now these open channel flows are relevant for natural channels like this. This is a natural channel formed by nature. It may be a river or it may be a creek or it may be a stream, natural stream. Then streams, creeks, floods, whenever there is a flood, the flood water will be flowing. So that also comes under the category of a natural open channel flow. Then the engineered channels, that means the channels which we construct for our application, for our usage, to convey the liquid from one place to the other, apart from the pipe flow, open channel flows. This is a channel which is constructed. This is a lined channel which brings water from a source to a destination point where it is used. Now the water can be used either for power generation or irrigation or for industry or domestic use. So that is the engineered or artificial channel, man-made channel. Canals, sewer lines where the wastewater flows, culverts. The culverts can be either full or partial. Culverts are meant to convey the storm water. Whenever there is a heavy rain, the rainwater will be flowing underneath the bridge or highway. Storm drains, freshwater aqueducts. Aqueduct is a structure which is constructed near the junction of a natural stream and an artificial canal. Irrigation canals, drainage ditches, all these things come under the category of artificial or man-made channels. So in an open channel, the velocity will be more important and it will be zero at the bottom and at the sides. If you consider any channel, when the water is flowing in it, so all along the bed and all along the sides, there will not be any movement. Why? It is due to no slip condition. What is no slip condition in fluid mechanics? The velocity of the fluid adjacent to the boundary will be same as the velocity of the boundary. Now here the boundary is fixed, so the boundary is not moving. Therefore, the velocity of fluid or liquid which is adjacent to the boundary will have the same velocity, that is zero velocity. So this is called as the so-called no slip condition. It is a very powerful boundary condition in all fluid mechanics problems. So due to that, the velocity will be zero. So you can see here, this is the velocity lines. So all along this, the velocity is zero. All along that, the velocity is zero. As you proceed towards the free surface, the velocity increases. So the velocity is approximately constant all along this line, and the magnitude of that velocity is 0.5, maybe meters per second or feet per second. So you can see there will be a maximum velocity not exactly at the free surface but slightly below the free surface. The reason is, at the free surface there will be a lot of debris and the air may be blowing in the opposite direction. So that will offer resistance and will reduce the velocity at the free surface. Otherwise, if you just take a cross section and draw the velocity, it should be in fact like this. Maximum velocity here, zero velocity here. But in reality, the maximum velocity will not be at the free surface but slightly below the free surface. So this is the maximum velocity, slightly below the free surface. And then the velocity also varies in the streamwise direction, that is in this direction. This is the streamwise direction, perpendicular to the plane of the board. So the velocity will be varying in this direction, and it may also have a transverse direction. So therefore, the flow is always three-dimensional. The flow is always three-dimensional. But for our analysis, we will assume only one-dimensional approximation for all practical purposes. To solve the practical problems, we consider the velocity to be varying only in one direction. So that is the simplification which we make. So as I was telling, there is a similarity as well as a difference between the pipe flow and the open channel flow. So let us see what are the things that make a pipe flow and an open channel flow. Now this is a pipe in which flow is taking place. This may be sloping like this or sloping in the other direction, or it may also be horizontal. Similarly, this is a channel which is shown with sloping downwards in the direction of flow. So what are the things that differ in between? What is the difference in between these two? Let us see. In the case of pipe flow, there will not be any free surface. It is under pressure. Whereas in the case of open channel flow, you can see this is the water surface. So this is the free surface. It is exposed to atmosphere. So the presence of a free surface is the characteristic feature of an open channel flow. Flow is under pressure, whereas the pressure here in the case of open channel flows is hydrostatic. What is hydrostatic law of pressure? P is equal to, yes, P is equal to gamma times Y, where Y is the depth of the point under consideration below the free surface. So in that figure, if you take this point, this depth is Y1, so the pressure here is gamma times Y1. If this depth is Y2, the pressure here is gamma times Y2. So that is hydrostatic pressure. Then, in the case of a pipe flow, In order to get the hydraulic gradient line, we can insert a number of piezometer tubes. So this is a piezometric tube. This is a piezometric tube. So when you insert a piezometric tube in a pipe, the liquid level will rise in it. To what extent it will rise? It will rise to certain extent which is given by the sum of the datum head and the pressure head. Similarly, at the other point also the water will rise to an extent equal to the datum head plus pressure head. So the line joining the water levels in the piezometric tubes attached to a pipeline will give you directly the hydraulic gradient line. In case of free surface flows, that is open channel flows, the water surface itself is the hydraulic gradient line. Because if I take this as the datum, so this is the datum head and this is the pressure head. Because here the pressure is atmospheric. Similarly, if I take another point here, this is the datum head and this is the pressure head. So this is pressure plus datum, that is the water surface. So in the case of pipes, the hydraulic gradient line is given by the line joining the water levels in the piezometric tubes. In the case of free surface flows, it is the water surface line itself. And how about the total energy line? The total energy line is one velocity head above the hydraulic gradient line, because total energy is given by P by gamma plus Z plus V square by 2G. So this is the hydraulic gradient and this is the velocity head. So in the case of pipe flow, TEL is above HGL by a value V square by 2G. And in the case of open channel flows also the same thing. So here also same thing. Then when you consider the pipe flow, if you take different points, the pressure will be varying. So there will be a pressure difference between any 2 points in the direction of flow. Pressure will be changing. Whereas here, in the case of open channel flows, the pressure is constant along the free surface. And what is the magnitude of that constant pressure? What is the pressure on the free surface? It is atmospheric pressure. The pressure is atmospheric pressure. Then the pipe flows pipes can be sloping in any direction. It can be horizontal, it can slope downwards in the direction of flow, or it can slope upwards in the direction of flow. We have seen earlier, if suppose there is a pipe the flow can take place in this direction. It is not necessary that the flow always take place when the pipe is oriented downwards. The direction will depend upon the difference between the total energy so if H2 is less than H1, the flow will be taking in that direction, from higher energy to lower energy. So if H1 is higher, which H is again equal to P by gamma plus V square by 2G plus Z. Whereas in the case of open channel flows, the flow is possible only when it slopes down in the direction of flow. Why? When it is sloping down, then there will be a component of the sulfate. The sulfate will be acting in this direction, downwards, and the component of sulfate will be acting in this direction. So this component will be compensating the resistance, frictional resistance. So only then the flow is possible. Otherwise, it is not possible. So after considering the difference between a pipe flow and an open channel flow, let us proceed towards the classification of open channel flows. Now in pipe flow we have seen the flows are classified based upon the variations of velocity with respect to time. Similarly with respect to space. So here also the open channel flows are classified based upon the temporal variations, that means the variations with respect to time. So they are classified as steady flow and unsteady flow. What is steady flow? Steady flow means the velocities and the depth at any given point in the open channel flow will be constant. They will not change with time. So if I consider an open channel like this, so if I consider any section here, so at this section with respect to time, the velocity, if it is constant, it is not changing with time, then we will call it as steady flow. On the other hand, if it is varies with time, then it is an unsteady flow. Can you give me an example of unsteady flow? Give me an example of unsteady flow. The situation where the velocity changes with time or the water level changes with time. Whenever there is a rain, storm, so what will happen initially? The water level will be less. So as the rain water enters into the channel, the stage of the water will raise. So there will be a change in the velocity. So that is an unsteady flow. So the natural flows or flows in natural streams, rivers, during flood times is an unsteady flow. Then the other classification is based on the variations with respect to space, the distance. So according to the distance, with respect to the distance, the flows are classified as uniform or non-uniform. Uniform, gradually varied and non-uniform. Why we are calling it as gradually varied and non-uniform is because unlike in pipes, in the case of open channels, the variations with respect to distance can be over a long distance or within a short distance. So if the variations are over a longer distance, then it is called as a gradually varied flow. But if the variations are within a short distance, they are called as rapidly varied flows. So in non-uniform flow, we have two categories: gradually varied flow, rapidly varied flow. So a uniform flow is the one where the velocity is constant at different sections. If you consider one section here, another section there, another section there, at all these points, the depth is same. So if the cross section is same, if the cross section is not changing, so naturally velocity will be area. What is the relationship between discharge, area and velocity? The continuity equation. Q is equal to A into V. Q is A into V. So when A, the cross-sectional area, is not changing, then V will be constant for a given Q. For a given Q, if area is not changing, the velocity will not change. So area means if I take a rectangle, B into Y. This is the area. So if the B and Y are constant, automatically V is constant. So that is a uniform flow. So in the case of a uniform flow, the depth remains constant throughout the direction of flow. Uniform velocity at a given instant of time does not change with respect to distance along the length of the channel at a particular time. So, gradually varied and rapidly varied. And in addition to these types of flows, there is another classification as in pipe flows, laminar and turbulent. So, same criteria. Laminar means viscous flows. Viscous flow is more predominant compared to inertia flow. Turbulent flow, it is a mixing. Inertial effects are more predominant. So the distinction between laminar and turbulent flows will be based upon the magnitude of Reynolds number. The Reynolds number is defined as usual. So I was telling about the gradually varied flow and rapidly varied flow. How and why there will be a change in the distance or in the depth of flow when flow is taking place, unless otherwise you put some obstruction, there will not be any change. So the change in depth will be happening only whenever there are obstructions or change in the cross section. So either there is an obstruction with the same cross section throughout, or from one section to another section if there is a change in the cross sectional area. So then this will be causing non-uniform flow. Now rapidly varied flow, you can see here in this figure, there is a gradually sloping channel with a sudden drop and again a gradually sloping channel. So in the sloping channel, as the flow progresses, the depth will vary, and the depth will be constant, uniform, and as it approaches this drop, there will be a change, because from this constant depth, it has to come to this depth. So there must be a change, a transition in the depth, a change in the depth. So that will be gradually happening. Now when you come to this point, which we will call as a brink, here the depth suddenly changes. So within a short distance, the depth changes. So this is called as the rapidly varied flow. Again, gradually varied flow, uniform flow. So normally, gradually varied flow will be connecting a uniform flow and a rapidly varied flow. So gradually varied flow is a transition between uniform and rapidly varied flow. Let us proceed further. This already I told, and we need not discuss about this influence of Reynolds number. You know, this is how we define Reynolds number. Reynolds number is ratio of inertia forces to viscous forces. Rho V R by mu. In fact, the definition of Reynolds number is rho into velocity into some characteristic dimension. In case of pipe flow, we have taken the diameter, but here we will take what is known as some other parameter, either depth of flow or some other thing. So rho is the density, mu is the viscosity, dynamic viscosity, or we can write it in terms of kinematic viscosity also. So as I was telling, in the case of pipe flows, this was diameter. Now in this case, it can be the depth of flow or the hydraulic radius. Hydraulic radius is area divided by, what is P? P is vectored perimeter. So A is the cross-sectional area, P is the vectored perimeter. In case of pipe flow, what is the value of R? R for pipes is equal to R for pipes is equal to, what is the area? Area is pi d square by 4 divided by, what is the wetted perimeter for a pipe flow? The flow will be full. So what is the perimeter? Pi d. So it will be d by 4. R in case of pipe flow will be d by 4. Before proceeding further, let us take or understand some standard terminology, the terms which we use in our definitions, in our understanding. So, the first one is the channel section. Channel section is referred as A. So, A is the cross-sectional area. So, the cross-sectional area is always taken normal to the flow direction. So, if the open channel is sloping in this direction, so this is the direction of flow. So, normal to this, what is the area? So, this is the area of flow. Depth of flow. Depth of flow, y, is the vertical distance of the lower point of the channel section from the free surface. So, it is the vertical distance. It is not normal to the channel. You can see here. If you have a channel which is sloping like this, a channel which is sloping like this, so this is the free surface. There are two things. One is the vertical direction, the other is the normal direction. So, this is what is called as y. It is the vertical distance between the free surface and the lower part. So, that is y, depth of flow. Then, depth of flow section is this one. Depth of flow section is that one. Now, when we want to calculate the discharge, Q is area into velocity. Say if we take a rectangular channel, if I take a rectangular channel B, so what is the area equation for area for a rectangle? B into depth. Which depth we have to take? Shall we have to take y or d? Shall we have to take d or y? D, because velocity is in this direction. Velocity is in the direction. So, area is always normal to the velocity. So, normal to the velocity means d. So, B into d into V will give you the discharge. Then, the stage of flow is the elevation or vertical distance of the free surface above a specific datum. I can choose a datum like this. So, this is the stage Z. This is the stage here, capital Z. Suppose if it is a horizontal channel, then I can take this as the datum. So, this itself will become the stage. Then, top width. Why a top width should be considered? Because in case of rectangular channels, both the width at the top and at the bottom bed width, they are same. If you take a rectangular channel, this is the bed width, and this is the water level. So both are same. Both are same. But if you take any other section, say a trapezoidal section, so this is the bed width and this is the free surface and this is the top width. That is the top width. So bed width and top width are not same. Similarly, a triangular section also. If you take a pipe where flow is not full, this is also an open channel flow, a free surface flow. So this is the top width. So top width is the width of the channel at the free surface. Flow area is cross-sectional area of flow normal to the direction of flow. Then wetted perimeter is this. All along the contact surface. See, this is the wetted perimeter. This is the wetted perimeter. So what is the expression for wetted perimeter in case of rectangle? It is B plus twice the depth. Here B plus twice the sloping length. So normally the sloping length is designated 1 in Z. So if this is Y, so what will be this value? ZY. This is again ZY. So here for a trapezoidal channel, the area will be BY plus area of two triangles, twice into half Y ZY. Half. So this is area for a trapezoidal channel is equal to BY plus ZY square. Similarly, you can calculate the wetted perimeter. The one point you have to remember, the wetted perimeter does not include the free surface. It does not include the free surface. It is only B plus 2D. Then we define what is known as a prismatic channel. A prismatic channel is a channel having the same cross section and bottom slope throughout. So such a channel is called as a prismatic channel. A non-prismatic channel means a channel where either the cross section may change or from some point onwards the slope may also change. So that is a non-prismatic channel. Let us look at some standard geometric open channel sections. A pipe with a free surface. So if your free surface is here, the area, if the radius is R, capital R, then the area is given by R squared into theta minus sin theta cos theta. Then P is equal to 2R theta. P is equal to, if this angle is theta, so it is, this is theta, so 2R theta. The total is 360 degrees. Then a trapezoidal, R is equal to A by P. A rectangle. Rectangle is simple, area and wetted perimeter. So after learning some terminology and then identifying certain standard geometric sections, channel sections, let us proceed how the velocity varies within a channel and how the pressure varies. So, velocity variation and pressure variation. In our topics for discussion, we have considered the next topic as velocity distribution and pressure distribution. So, here I have shown some figures which indicate how the velocity will be varying. You can see in a triangular channel, these are the lines of equal velocity. Lines of equal velocity. Lines of equal velocity. So, a line of equal velocity is called as isowell. Isowell. Iso means constant. Well means velocity. So, lines of constant velocity are called as isowells. Then, how the pressure varies? Now, we have seen when comparing the open channel flow and the pipe flow, we have learned that the pressure will be throughout atmospheric pressure. Now, that is not always true. To start with, it may be right, it may appear to be correct to you, but there are certain conditions applied. So, if it is a parallel horizontal flow, then the depth will be throughout same. Parallel horizontal. So, then the pressure is always equal to gamma times y. Suppose it is a convex flow in a sloping channel, then the pressure will be more than atmospheric pressure. So, if you introduce a piezometer, it will raise above the free, this is the free surface, it will raise above the free surface. So, in this case, the flow will be more than, the pressure will be more than hydrostatic pressure. In the case of a concave flow, it will be less than atmospheric pressure because there will be gravitational pull acting. So, due to that, the water surface will, the pressure will fall down, will be less than the atmospheric pressure. So, in the case of a horizontal parallel flow, it is purely hydrostatic, and in the case of convex flow, it is greater than hydrostatic, and in the case of concave flow, it is less than hydrostatic. Now, when we come to the normal natural channels, parallel flow but in a sloping channel, then what will happen? Let us see. The pressure distribution will obviously not hydrostatic. It differs from hydrostatic. But for under certain conditions, we can assume the flow to be hydrostatic. So, let us assume a sloping channel and flow taking place. Take a small element. Let the velocity be uniform at a section and the flow is parallel to the channel bottom. So, we will consider a free body of a column, and that free body we will consider as normal to the channel bottom. So, what is the weight of the fluid in this free body? Weight is given by gamma unit weight multiplied by volume. How do we define unit weight? Unit weight is weight per unit volume. So, weight by volume is gamma. So, weight by volume multiplied by volume will give you the weight, which is itself is the force. So, that is acting downwards. So, what is the component in this direction? That is vertically downwards. Vertically downwards. So, what is its component in this direction? It will be that multiplied by cos theta. So, gamma d into delta A is the force acting vertically downwards. So, in a direction normal to the channel bottom, it will be gamma d delta A cos theta. So, this is the weight. Weight is obviously equal to the force. Weight and force are one and the same. So, how do you get pressure from force? What is the relationship between pressure and force? Pressure is force by area. So, what is the area? Area is delta A. So, what is the pressure at the bottom? Gamma d cos theta, gamma d cos theta, where d is measured normal to the channel bottom. D is measured normal to channel bottom. So here I will exaggerate the figures. So this is theta, d is y times cos theta, y times cos theta. So if I substitute for d y cos theta in this equation, I will be getting this as gamma y cos theta into cos theta. So that is gamma y cos square theta. So gamma y cos square theta is the pressure. Now hydrostatic means what? According to our definition, hydrostatic pressure means P is equal to gamma times the depth of the point below the free surface. That is gamma times y. So gamma times y is the hydrostatic pressure. But here is P is gamma y cos square theta. Gamma y cos square theta. Is it more than hydrostatic or less than hydrostatic? You have to find out whether cos square theta and 1, compare these two, which will be more? Cos square theta will be more than 1 or less than 1? Cos square theta is always less than 1. So in a sloping channel, the pressure will be less than hydrostatic pressure. But when you take a very small slope, cos theta is almost equal to 1 and the pressure will be therefore gamma y. So we can use for small slopes the pressure as gamma y itself, hydrostatic pressure itself. Why we are considering this point? Because this is required in all our analysis. In the flow, open channel flow analysis, we have to find out the pressures, force, pressure, etc., etc. So in all situations, we have to make this assumption. So this will be valid only when the slope will be small. Now here I have given you a table for your reference and for the purpose of working out the problems. For standard channel sections, the area, the wetted perimeter, the hydraulic radius, the top width and the hydraulic depth. Now there is a difference between hydraulic radius and hydraulic depth. The hydraulic depth is the ratio of area by top width. Hydraulic radius is area by wetted perimeter. Both will have the dimensions of length. L square, L, 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 L. So B is the width, bed width, Y is the depth, B is the bed width, Y is the depth. So the area will be product of B and Y. Wetted perimeter B plus 2Y. And hydraulic radius is BY area divided by B plus 2Y. Top width. Top width will be same as bed width in case of a rectangular channel. And the hydraulic depth will be same as the depth of flow in the case of a rectangular channel, because A is B into Y divided by top width is B, so this is equal to Y. Whereas in trapezoidal channel it will not be so, it will differ. So this is the trapezoidal channel, By plus Zy square, or taking Y outside, Y into B plus Zy. So in a trapezoidal channel, this is how it will be. This is the channel, this is B, this is Y, this is T, and this is 1 and this is Z. This is 1 in Z. I can say when Z is substituted as 0, it will become a rectangular channel. A trapezoidal channel where Z is equal to 0 will give you a rectangular channel. You substitute Z is equal to 0 here. So what will be this value? A is equal to By. Similarly, if I substitute Z is equal to 0, P is equal to B plus 2Y. So, a triangular channel, a circular channel. So we will be using these things when we discuss more about the hydraulic sections, efficient hydraulic sections. Now let us proceed for the basic equations in open channel flows. What are the basic equations? There are many equations which describe the velocity of flow in an open channel. Open channel flows are analyzed with the help of one of the several empirical equations. Empirical equation means an equation which is developed based on the theory and the field observations or the laboratory observations. An empirical equation is the one which is developed from a theoretical background with the constants and or the exponents which are involved being decided through field studies and observations. So various empirical equations are given by different investigators, but we consider two most commonly used equations. They are Chezy's equation and the Manning's equation. Chezy is a French engineer and Manning's is an Irish engineer. Chezy has developed the equation, in fact he has derived it from the fundamentals in 1789, and Manning's equation is given somewhere in 1880s. So Chezy's equation was developed in 1768. So these are some of the assumptions involved in the development or derivation of Chezy's equation. We will take the help of continuity equation, Q is equal to AV, and then we consider the channel to be sloping with a very little slope, small slope. Why this assumption is required? In order to write down the pressure as hydrostatic pressure. P is equal to gamma y. When the slope is not small, I cannot write P is equal to gamma y. I have to introduce P is equal to gamma y cos squared theta. So the analysis becomes complicated. Then the channel is prismatic. That means the cross section is constant along the length. Chezy's equation is derived by evaluating the forces along the channel by considering a control volume and writing the force balance equation. So the force acting, force due to pressure, force due to the weight, and the bottom resistance, frictional resistance. So the force balance equation is written. I will be skipping the derivation for the time being, and ultimately I will give the equation. So this is the equation which we have. The velocity is given according to Chezy's formula or Chezy's equation. V is equal to C root R SF, where SF indicates the slope of the energy line. Slope of the energy line. And C, which is called the Cheggy's constant, is given by square root of 8G by F, where F is our Darcy-Weisbach friction factor. So, when the flow is uniform, then what will happen in case of uniform flow? This is the channel bottom. This is the water surface. This is the hydraulic gradient line. This is the total energy line. So this is TEL. This is hydraulic gradient line or water surface, and this is the bottom. So the slope is S0. Now because the depth is same, HGL will be parallel to bottom. So if I call this as SW, because the depth is same and the cross section is not changing, the velocity will be the same throughout. So the velocity head will be same throughout. So total energy line, which is HGL plus one velocity head above it, so this will also be parallel. So the slope of total energy line is SF, slope of water surface line is SW, and the channel bottom slope is S0. So in the case of uniform flow, SF is equal to SW is equal to S0. So we can replace SF by S0. So that is Cheggy's equation. Manning's equation is similar to that with a slight difference. Manning's equation is V is equal to 1 by N R to the power of 2/3 SF to the power of half. So here in case of R being to the power of half, according to Cheggy's, here we are getting R to the power of 2/3. So that is the difference. Here N is called as Manning's coefficient, is also referred as rugosity coefficient. So for a uniform flow, SF is replaced by S0. So this is Cheggy's equation and this is Manning's equation. Normally, when we carry out the designs, Manning's equation is mostly considered because of practical relevance and proven methodology. So let us stop today at this stage. Thank you.